This video is going to go through the process to find the zeros of a polynomial function. Your zeros, otherwise known as your roots, and also your solutions to the polynomial, are where your graph either crosses over the x-axis, or if they're non-real, then we have to do some calculation to find the complex roots. The fundamental theorem of algebra tells us that all solutions are equal to the highest degree of your polynomial. So the nth degree, which is the largest exponent, is equal to the number of solutions. It's important in this next note to say that the finding of the zeros is not all of them are going to be real numbers, right? Your zeros can be real, rational or irrational numbers, so whole numbers, fractions, radicals, all of those options, or they can be imaginary and contain the value of I. Okay, so looking at some of the examples below here, we have a fourth degree polynomial here. So if it's fourth degree, that means the exponent on this will be 4, so the number of roots that would actually be found is equal to 4. What are the real zeros? Well, if we look at our graph, our zeros are the values where your graph is touching or going through the x-axis. So in this case, x is equal to -2 and x is equal to +2. We know, though, that our number of roots is equal to 4, but we only have two values, -2 and 2. So what's important to note here is multiplicity. Multiplicity is the number of times that an answer actually occurs. Okay, so in this case, the behavior of a graph, when it changes from a decreasing to an increasing interval and is tangent to the x-axis here, that means that that value of -2 occurs twice. So this has a multiplicity of 2. In this, at +2, also decreases and then increases. So that minimum point is tangent to the x-axis, making +2 also have a multiplicity of 2. So they occur twice. So there is your total number of 4 zeros. 2 at -2, 2 at +2. It is important to also know that imaginary roots are also possible, but can't be seen on the graph. So in this case, if we have a fourth degree polynomial where -2 and 2 occurred twice, there's our 4 roots. We don't have any more options for our imaginary solutions. So our imaginary solutions would then just be 0. We don't have any. Another side thing is imaginary roots always come in pairs. So if we don't have any, that's fine, but we are either then going to have 2 or 4 or 6 or 8 imaginary solutions, always an even value. Right, in graph number 2, you notice that we're only hitting the x-axis at one point, and that's at +3. If we're told that this polynomial is a fourth degree polynomial, that means that the number of roots will equal 4, just like the last one. But the behavior for this polynomial is a bit different. We can see that there's only one solution at 3. But again, because it is tangent to that x-axis, decreasing then increasing, tangent sitting right on top of that x-axis, that means that this has a multiplicity of 2 that is occurring twice. Well, if 3 is occurring twice, but we have a total of 4 actual roots, that means that we end up with 2 leftover imaginary roots. So we get this from taking the degree minus the real roots that we have. That we can see on the graph, and that's going to equal whatever we have left over for the imaginary values. Number 3, this final picture, we have, you notice this is actually hitting the x-axis 4 different times. This is a degree of 5, as we're told, so the total number of roots should equal 5. So let's go through our list. First, root on the left is, our first 0 is -3. It is not a multiplicity of 2 because it is going right through the x-axis. At -1, we have another root, and then at +2, we have a third root. At 3, you'll notice that, again, just like the others, it is tangent to that x-axis. So at 3, this has a multiplicity of 2. So that value of 3 is occurring twice. If we add up all of these options, 1 at -3, 1 at -1, 1 at 2, and 2 of them at 3, then we have a total of 5 already, so there is nothing left for imaginary roots. For the next couple of questions, we are going to name all of the possible real and imaginary zeros and their multiplicity based on the factored equation. What do we know about factors? Remember that our factors end up giving us our solutions. So each of these factors, if we set them equal to 0, we get our actual zeros or our roots. So x plus 1 is equal to 0, so x is equal to -1. X plus 2 is equal to 0, so x equals -2. Our third root, x plus 2 again is equal to 0, so x is -2. And then x minus 3 equals 0, so x is equal to 3. Our values for our solutions, as we see here written out, there's 4 of them. But x is equal to 1, x is equal to -2, and has a multiplicity of 2. And also x is equal to 3. So those are the 3 solutions, or 4 solutions really, because you have 4 factors, you end up with 4 solutions. In number 5, we're going to set these factors equal to 0. So x minus 1 is equal to 0. When we solve this, we should recognize that it is the difference of 2 squares. So we have x minus 1, x plus 1. So in this case, x minus 1 is equal to 0, so x equals 1, and x plus 1 equals 0, so x is -1. In the second factor, x squared plus 1 equals 0, this is not the difference of 2 squares, but we can set this equal to -1. And as an operation to unsquare, we are going to take the square root of both sides. When we take the square root of both sides, we need to remember a plus minus. So on the left-hand side, square root of x squared is x. And on this side, we get plus or minus the square root of -1. We know and should recall that square root of -1 is I, so we end up with 2 solutions, plus or minus I. This gives us 4 total solutions, 1, -1, and plus or minus I. Of those 4, no multiplicities, but we have 4 separate solutions, and the degree of our original polynomial is 4, so we should have those 4 solutions. In number 6, we have 3 separate factors. However, this one is occurring twice. So that means that x plus 1 is equal to 0 twice. So x equals -1 has a multiplicity of 2. X plus 2 equals 0, so x equals -2. And x minus 2 equals 0, so x is equal to 2. So our 4 solutions for this are -1 twice, -2, and +2. Using your graphing calculator and knowing all of this about our zeros, we are going to look at the next example on which we are going to graph and find all of our solutions. On your graphing calculator, in y equals, we are going to put in our equation of x to the fourth minus 5x squared and minus 36. Oh, this isn't working. There we go. And we get a graph that we just can't see the whole thing for. We don't really need the whole thing, but just to show you the window, if I change the y minimum, I'm going to change it to negative 60 so you can see what the whole thing looks like. We are only interested in our roots and our zeros, which occur on the x-axis. So this was negative 10. I'm going to make this positive 10. This is positive 10. And I made this negative 60 just to kind of show you what the rest of this graph looks like. So our whole graph, I'll draw a rough sketch, looks something like this. How many solutions or number of roots do we actually have for this example? We should have the degree, which is 4, so we end up with 4 roots. How many of them are real? Looking at our graph, we only have 2 real solutions, one here that's negative and one here that is positive. So because of that, our real root, our degree minus the real number of roots, in this case, will give us the number of imaginary, which is 2. There are 2 imaginary roots for this particular problem. On your calculator, we have found before, you can go to your table, but you also did some work with the graphing calculator on how to find these solutions, these 2 solutions on your calculator. Where this is hitting the x-axis is at negative 3, and this one is 3. So your 2 x-intercepts are negative 3, 0, and 3, 0. So just below here are zeros. X equals negative 3, and x is equal to 3. From our zeros, right, we get these from the calculator. The remaining 2 zeros we are going to find, but we are going to find those by using some synthetic division. The factors created from x minus 3 and x equals 3 and x equals negative 3 are x plus 3 and x minus 3. From your calculator, which is your first step, you're getting your zeros. Your second step is to use synthetic division. Right, so step 1, we're going to get this from our calculator. Put that right there. Step 2, we are going to use synthetic division. Okay, synthetic division with both of our zeros. So first we're going to take negative 3 and use synthetic division with our coefficients, which are 1, 0, negative 5, 0, and negative 36. Bring down the 1. This becomes negative 3. This will be 9, negative 12, and positive 36. When we divide, if you remember, with a 0, right, at negative 3, it will come out to be a remainder of 0. If it does not, then something is wrong, so you need to go back. Okay, the second root, or 0, which is positive 3, we are going to add on and continue our synthetic division with the positive 3. This is 3, that becomes 0. This is 4, and this is 12. So that works again, having a remainder of 0. From here, our third step is going to be to solve the remaining Oops. Polynomial. The remaining polynomial is coming from these coefficients. Those coefficients are going to give us a polynomial of 1x squared plus 4. And I know it's x squared because we started off with x to the fourth, and every time you do a synthetic division, the degree comes down one more. So now to solve this, like we did before, I'm going to move the negative 4 over, take the square root of both sides, and then x is equal to plus or minus 2i. So our remaining solutions, remaining zeros, become plus or minus 2i. So the factored form of our polynomial, and this, by the way, generates a factor. So I can write it up here, x squared plus 4, right? That becomes that remaining factor. So the factored form of our polynomial, from each of the zeros, we get x plus 3, we get x minus 3, and then from what we have done with synthetic division, we get x squared plus 4. That is our factored form. Our final answer for all of the roots becomes x equals negative 3, x equals positive 3, and x equals plus or minus 2i, which I'm just going to write out separately to show you that we do get 4 roots because this is a fourth degree polynomial. Okay, this, or you could write it as x equals plus or minus 2i. I wrote it out so you can see that there are 4 actual solutions. Let's look at one more of these together. We're going to look at number 2. And first thing we're going to do, graph on our calculator. Go into y equals. We're going to clear out the equation that's in there. And we're going to write x cubed minus 11x plus 40x minus 50. And I'm going to bring this back to a standard window so we could see it better. We don't need that negative 60. Or maybe we do. But it does count the, let's see, let's change the y minimum to negative 30. And we'll see that it will cross down here real low. But we're not so much interested in that particular point. What we're interested in is this real 0. That's the real 0 we want. So on your calculator, you are going to find the intersection point. You can graph y equals 0, find your intersection, and that point comes out to be 5, 0. You can either get that from the table or by doing your intersection with y equals 0. The number of roots for this problem, we should have 3. Right, that is our degree for that polynomial. We need 3 roots. How many of them are real? Only 1. Right, only one of them is real. That's the 5. So that means we have a remaining 2 answers that will be imaginary. So our zeros from our calculator, x is equal to 5. Right, again, we're getting this from the calculator. So our factors from that become x minus 5. We now use that 5 with synthetic division. Okay, because we know 5x minus 5 is a factor, so when we do synthetic division with 5, we should get a remainder of 0 and then a polynomial to factor. So our coefficients are 1, negative 11, 40, and negative 50. We don't need to skip any or have any placeholders. We have everything. So we bring down the 1, and we multiply. Add this up, we get negative 6. So we end up with negative 30, which makes this 10, making this 50. We're finally a remainder of 0. From this synthetic division, we end up with the polynomial that is x squared minus 6x plus 10. We set this equal to 0. We now solve. This is not factorable. So one of your methods for solving quadratics when it's not factorable is to use the quadratic formula. Our quadratic formula tells us to take the opposite of b, plus or minus b squared minus 4 times a times c all over 2a. Simplifying the numerator, our discriminant underneath that radical comes out to be negative 4 all over 2. So that negative 4 underneath the radical means that we are going to have a complex imaginary root, right? We have, and we should have 2 of them. So that's good. So we're going to change this to be 6 plus or minus 2i over 2, which simplifies nicely to be 3 plus or minus I. Those are the remaining 2 imaginary solutions. So our final number of solutions to finish this up, all of our roots, x is equal to 5, and x equals 3 plus I, and x equals 3 minus I. Last but not least, just to be very clear, this, when we rewrite it, this becomes a factor. Okay. So our 2 factors are x minus 5 and x squared minus 6x plus 10. Every time we do synthetic division, what we end up with will be a factor and written in factored form. Okay, last but not least, let's do one more for good luck. Plotting this is a long one to put in your calculator, but I'm not going to do that. I'm just going to show you what it looks like. This is now crossing the x-axis twice at negative 2, 0, and this point here is at 1, 0. The degree of this polynomial is 5, so the number of roots we have is 5. The number of real roots is 3. Why is it 3? Because this one here has a multiplicity of 2. It is tangent to the x-axis. It counts twice. So 1 is counting twice, and negative 2 is counting once. We call that, by the way, the multiplicity. We call that number a double root. What's left over? We end up with 2 imaginary roots. Our zeros are negative 2 and x equals 1, which, as I just said, is called a double root because it counts twice. It has a multiplicity of 2, and it has a fancy name called a double root. Our factors from these terms become x plus 2. 1 being a double root is x minus 1, but since it's doubled, we are going to square it because it repeats twice. So how many times we do synthetic division? We actually set this up for 3 numbers. I'm going to start with negative 2. The coefficients are 1. X to the 4th is missing, so we need a placeholder at 0. And then x cubed has a coefficient of 1, then 2, negative 12, and 8. Bring down your first term and multiply. Going across, this is 5, negative 10, this is negative 8, so 16. This is 4, brings us to negative 8, and a remainder of 0. We now need to do our double root of 1 twice because you have multiplicity. So we are going to start off first. 1 is 1, this is negative 1, times 1, add down is 4. This is a 4, negative 4, -4, and 0. As I said before, we need to do 1 again, right? And the reason we do that, you must do twice because of multiplicity. All right, so we bring down the 1 to finish this up, and then this is a 1. Add that up, you get 0. Add 4. This is 4, a remainder of 0. So our final polynomial, we have divided 3 times synthetically. So we've brought down the degree of 5 in our original problem. Bringing it down 3 times brings this polynomial finally down to be x squared plus 4. And as we saw before, that x squared plus 4 is a factor. So I'm going to put that right here. That is your remaining factor to this polynomial. Okay, finishing up to get our last imaginary solutions. X squared is equal to -4. Square root both sides. X ends up equaling plus minus 2i. So all of our roots as a final list become -2, 1, 1, 2i, and -2i. If you wrote it out, you could write x equals -2, x equals 1, multiplicity of 2, and x equals plus minus 2i if you wanted to shorten it up a little bit, but listing them all out is a great conclusion. You will have homework problems very similar to this. Again, your first step is to graph, get your real numbers off your calculator, use those values synthetically to then finally solve what is the polynomial that is remaining.